Today's speaker is John Eggert. He's Senior Sales and Marketing Manager from Velodyne LiDAR. He has more than 20 years industry experience, particularly focused on the automobile industry. Let's welcome John to our conference.
Thank you very much, Simon. I appreciate the opportunity to tell you about our technology at Velodyne today. High-definition 3D LiDAR. After the presentation today, we also have a demonstration of our LiDAR. I hope you'll be able to stick around for that, because it's kind of a fun technology, and I think it's definitely something you're going to see a lot of in the future. When you're my age, you've had the opportunity sometimes to work for a lot of great innovators in the industry. When I started in automotive, by the way, my background is about 25 years of automotive, from very low-tech carpeting to very high-tech. Our sensor design, we're a very small company, 60 people when I started over a year ago, but we actually entered some contests for self-driving and performed quite well early on. And it was out of that, our experience, that we learned to design what we thought was the ideal sensor for self-driving. So I'll focus a lot on self-driving today. I'm the automotive guy at Velodyne. But we'll also talk about some of the other applications of LiDAR as well. And then some of the future developments and challenges to make LiDAR commercialized. As you know, it's not commercialized today, widely commercialized. You might know us from the large sensor on top of the Google vehicles back in the day. That was a Velodyne sensor. But things have changed quite a bit since then. That sensor, I think, is still the gold standard for sensors, but we have a lot of things coming down the pipe that are even better. So we were founded in 1983 by David Hall. Initial capital, $200,000. We've been bootstrapped since then, so we're one of the oldest startup companies in the Silicon Valley. We haven't gone through our Series A yet. The first thing we did was subwoofers with minimal distortion, digital signal processing, 16,000 points per second, taking measurements off the cone of the speaker. And then through that, feeding into the driver to reduce distortion. Previously, if you listen to old subwoofers, you turn them up, you'd hear terrible distortion. And with the advent of this kind of speaker, now you can just feel that very deep bass, beating against your body. So David Hall likes to say that perhaps we helped introduce rap to the world, so please forgive us for that. But this was our first innovation. But David Hall's a very competitive guy. So a few years later, he also had a great deal of interest in electromechanical systems, and we entered a TV show called Robot Wars. Does anyone remember that one? These were battle bots. They would fight each other. And we actually entered with something called Drillzilla. So a very obvious name with a very obvious function. It would drill into the opponents. And we were the world runner-up for world champion 1 year. So you got a very competitive guy with a great background in digital signal processing, electromechanical systems. The next challenge for our company was participation in something called the DARPA Grand Challenge. Does anyone know what that was? Yeah, some of you are familiar with it. It was the first competition for self-driving cars, sponsored by the Department of Defense in 2004. And this little company, Velodyne, entered a stereo vision-based system. You can see the vehicle up there. It's called Digital Audio Drive. And we finished in third place, remarkably, which was the good news. The bad news is we only went 6 miles, so about 1/10 of the course. And so back then it was a very early stage technology, and not a lot of people were having success with it. And out of that, we invented the ideal sensor. I'll talk a little bit about that. Since then, we've established the first HDL64 sensor. You've seen that on top of the Google cars initially, but it's actually a lot more than that. We'll go into that. But out of that first driving challenge, when we used stereo vision cameras, we realized there were a lot of shortcomings to cameras. And so David and his team put their minds to what kind of sensor would be ideal. One of the key points was the sensor had to be immune to all lighting conditions, ambient lighting conditions. Because this contest was in the desert, you get low-angle sunlight, you get very deep shadows, very dark shadows. And so if you couldn't navigate your way around all sorts of lighting conditions, that was a problem. Self-driving also requires a very fast update rate. Unlike slower-moving ground robotics, a self-driving car has a very active environment and a very dangerous environment, so you have to constantly be aware of what's going on around you. Same thing with the resolution. You need a very high resolution sensor to accomplish that. We also felt that you need a maximum horizontal field of view. So camera vision, you would see in front of the vehicle, you know, a certain number of degrees, just the front of the vehicle. Whereas there'd be all obstacles and other things coming at you from every direction. So a 360-degree view of the world was optimal, we felt. And of course, false positives, that was another killer. If you look at any of these early DARPA challenges, you see cars would move a few feet, stop. Wait a while, then they might move a few more feet, stop. And so false positives will kill a self-driving vehicle. It will stop it in its tracks. So, based on the experience, the first challenge was immune to lighting conditions. We settled on LiDAR. At its core, LiDAR is a range measuring device. It measures distance. This is a very simple example of one where you've got a transmitter, laser typically, firing out a light pulse, hitting a target, and then a receiver, photodiode, catching that signal. And by the time of flight, you would know exactly how far away that object was. So you would know exactly what the distance was with the LiDAR system. That obviously wasn't enough for self-driving for us, so these were the kinds of innovations we came up with in 2004 to make it ideal for self-driving. We took a 2D LiDAR sensor, so essentially the rangefinder, but we added multiple lasers and detector systems. So instead of one laser and detector, scanning the environment through mechanical actuation, we had 64 in our first one, so 64 lasers and detectors. Obviously, greatly increasing the amount of data that you get and the resolution as well. We also introduced 360-degree rotation to the system. So again, you needed the widest possible horizontal field of view. 360-degree rotation with a brushless DC servo motor got us that. And probably the one key that is lost on a lot of LiDAR systems today, we hear in the news a lot of, what about flash LiDAR, what about optical phaser, right? In our estimation at this point, we think that still the only technology that has been proven good enough for self-driving activities is one laser matched to one detector. So every one of those channels has one laser firing very quickly, a matter of nanoseconds, and the detector listening for that very short period of time in that very specific area. And so by doing that, you maximize the signal-to-noise ratio, and you're able to get a very clean signal and very clear picture of what's around you for a pretty good range.
So is one detector actually associated with one receiver, or it could be receiving from another transmitter?
No, it's listening for, the one detector is listening for a very short period. It's on and off, only when that first laser is firing, when that mated laser is firing.
So one specific transmitter and one
exactly.
pair.
Collinearly aligned, so it's looking at a very specific spot as well for a reflection.
So then why do you need 64 if you're really only detecting one?
Well, I'll show you what's going on. Well, you can take a look at these. These pictures aren't great, but by having 64, you get a very high resolution picture around you. So the traditional system might have one line scanning. Imagine like a blind man with a cane reaching out and hitting something, knowing something is there. By having 64 firing all around you, you create a point cloud. And that's essentially a 3D model of the world around you, instantaneously. So you can imagine if you've got a self-driving car, if you've got a 3D model, you can have a different perspective. You can look above, and that helps with path planning. You can see all the routes, you can see all obstacles well ahead of time, as opposed to a camera where you're just seeing more or less 2 dimensions or 3D in a very low angle. So, yeah, that's why you have the 64 channels. A lot more resolution.
So you can see a bird's eye view also?
Yes, you can.
John, just a quick question. How would it be different from the Connect sensor?
Yeah, again, it's a resolution thing. You've got 64 lasers and detectors. You're creating a 3D. You're not just saying, is something there? Yes or no, very generally. Kind of like a radar, if you will. You're saying, what exactly is there? Or what's the shape of that thing there? What's the volume of that?
How many sensors do you have? Just one sensor?
We have 3 different products. I'll get to that in a moment.
One last question.
Sure.
So at any point of time, only one transmitter is active?
Yes.
Okay.
Right.
For the test, I think you have a single autonomous driving car, right? Self-driving car. But in the future, if put it into application, you have 1,000 cars, will they interfere? Say they all use LiDAR.
That is one of the challenges of LiDAR, and we have solutions that I can't really talk about today, but that is of course one of the challenges. Although with ours, again, you have collinearly aligned, listening very short period of time, so the amount of noise you're going to get is minimized. But yes, that's a very good point. That's something that...
I mean, the light has scattering, right?
Yep. Exactly. I mean, it does scatter.
Yeah, only after you want very high sensitivity.
Yeah, we've got a variety of things that we do to synchronize sensors, but again, I can't really speak to the specifics of that right now. So what were the results of that? So there was the DARPA Urban Challenge in 2007 that came out, and we were fortunate enough that our sensor placed first, or it was on the first place vehicle out of Carnegie Mellon University. That was a joint effort between Carnegie Mellon, General Motors, and Caterpillar. Remember those names. I think they're pretty key people in the self-driving world today. In second place was Stanford University, again using our sensor on top, and that was Sebastian Schrun's lab. So, you know where they ended up. They ended up at Google and other places as well. To your question about what sensors we do have, so we started with that HDL64. It was our highest resolution sensor, and today it's still kind of a gold standard for mapping and for self-driving cars. You've probably seen some self-drivers still with this big sensor on top of it because it is indeed the best. And a lot of people are still using this sensor for ground truthing. For example, camera-based systems will use our sensor to train the camera. So to tell the camera, yes, that is a line you're seeing on the ground. No, that isn't the line that you're seeing on the ground. So it's used to train camera-based artificial intelligence systems.
You mean a LiDAR can detect a line on the road?
Yeah, so we don't just have the XYZ data that we're giving you out of the sensor. We also have a calibrated reflectivity measurement. So how reflective is the surface? And I'll get into that a little bit later with some of the sample videos I show you, but it's something we really didn't realize the value of early on, but I think every self-driving, legitimate level 4 and above self-driving program on the planet is relying on reflectivity of the ground surface to see lines.
Sorry, share about the resolution. What kind of, say 100 meter, what kind of spatial resolution you can like? Like a centimeter or?
Yeah, it's well, this sensor is 2 centimeters. Accuracy is 2 centimeters.
2 centimeters.
Yeah, the accuracy of these ones are 3 centimeters approximately.
At what kind of distance?
The full range, 100 meters.
100. Oh, okay.
So after the HDL64 was introduced, we introduced the HDL32 sensor. It was an effort to reduce the form factor of the sensor. So we reduced the weight of it by an order of magnitude by going from this. You've probably seen that one. It's about like this. It's probably about 30 pounds, something like this, to the HDL32, which is this one. And this one still has pretty high resolutions, 32 lasers and detectors. And if you've seen the Ford vehicles, the Ford completely autonomous vehicles, they've used 4 of these on top of their car. So it's still a very high resolution sensor, good enough for self-driving. Also, it made implementation of these sensors on UAVs a possibility as well. So now drones are flying around with these things. So since that time, that was in 2011. In 2015, we introduced our smallest sensor yet. This is a VLP-16 sensor, or it's a dummy. But it, again, is another example of reduction in cost and form factor. This sensor here is 1/10 of the price of the HDL64. Its resolution is less. It's got 16 lasers and detectors, but it's still good enough resolution that it can do self-driving activities. I don't know if you've seen some of the self-driving shuttles around the area. There's one at Santa Clara University by a company called RO Robotics. I think that's it right there. But it's a self-driving shuttle. It's slower speeds. The resolution is sufficient. And of course, it makes it even easier to implement and payload requirements for drones. So even though our DNA is in self-driving, our biggest markets up until last year had nothing to do with self-driving. That was a very small piece of our business. The biggest part of our business was 3D mobile mapping. These are the guys who are making maps that allow self-driving. So companies like Kia here, that was actually bought out last year by BMW, Volkswagen, or Mercedes. They're obviously thinking about using high-definition 3D maps for self-driving. Similarly, Microsoft Bing, that was another company that was purchased by a robot taxi company looking to do self-driving, obviously. Google Street View. TomTom is a very familiar name for navigation systems. They have a lot of interesting products for self-driving as well. They actually take our 3D data, which is very high bandwidth, and compress it into a 2D product for self-driving. And literally everyone around the world who is doing mapping for self-driving, a company in Korea called Naver is doing 3D maps. In Japan, there's a company called Zenrin. China, of course, there's Tencent and Baidu doing that. So just about everyone doing mapping is using Velodyne LiDAR to generate 3D maps. Of course, there's the drone business as well. Small enough form factor. I've got a little video here to kind of demonstrate. Let's see if I can. This shows 3D LiDAR data taken from a drone, and it's overlaid with camera data, RGB data as well. And it's a North Shore, what is it, in Alaska, the pipelines. And this color is showing the elevation. So that's what you can do with LiDAR. You know exactly the distance of it. And it's created a 3D model of the pipelines. And in the winter, in the tundra thaws and freezes, so pipelines rise and fall. And so they need to have very precise measures of exactly what the elevation of these pipelines are. And again, because it's 3D LiDAR data, you can also take measurements of it. I think in the video here you show, you go right like that and immediately see 104 meters distance. So again, it's a 3D CAD model that you're generating just from one flyover with a LiDAR sensor. In some of the industrial applications, some of these might be familiar to you. You probably know Boston Dynamics, the Atlas robot. You've probably seen videos of that thing. It's using this up there is this sensor, our HDL32. It's the vision, doing 3D spatial perception for the robot. Lowe's, this is an interesting product. It's a concierge almost. You walk into these big box stores, you want to find a screw. It's a very frustrating experience, I'm sure you're all aware. But you ask the robot to lead you right there. Virtual reality. This was a virtual reality demonstration. It creates a 3D model and it perceives objects in space, moving through space. So this virtual reality game would show the football going through space and measure how accurate your passes were against a screen. Also used for, I've got a little video about this. This is a people tracking security application by Raytheon. And this is a port applications, loading and unloading of containers with very high accuracy. Yes?
What's the computing requirements? Like how many bits do you need to do this processing? I imagine that you must do it locally, right? Not from the cloud.
Yeah, well, yeah. We're streaming UDP packets over Ethernet with our sensor. So raw data at a rate of about megabyte per second with the smallest sensor, probably 8 to 10 with the largest sensor. So it's a lot of data that's streaming, but it's raw data.
Oh, so you need like a computer or a processor on board?
Yeah, to interpret what you're saying. Yeah, we'll give you XYZ data and we'll give you reflectivity from our sensor.
I see. So there's not like a special customized ASIC or something that's in your sensor?
Not at this point. There are ASICs, but not for that.
Your company's product different than Fonergy's LiDAR sensors?
That's one of the optical phased array sensors. Actually, the first generation sensor, the M8, was essentially a copy of this with eight sensors, and 8 lasers and detectors. The next generation solid state optical phased array. It's a great concept. It was demonstrated by DARPA last year, but in our opinion, and we've got a vested interest to make sure we're staying on top of the R&D in this field because we currently are the market leader. We haven't seen it demonstrated well enough to do self-driving tasks or any of these other tasks yet. So, it might be a technology of the future, but we'll see.
Any reason why Tesla doesn't want to use LiDAR? So there must be something.
I'm being recorded, so I can't say it.
See, the leader is Tesla, and they are not following with Velodyne, your stuff. And all the cars we see on Highway 280, I saw BMW also going this way, none of them have any shipping products. So to me, it seems like what your company is doing is just a lab project. Then until Tesla doesn't endorse it, it's just like being in a lab.
Well, it's important to make a distinction between what Tesla is doing and what other people in the market are doing. I'll show you some examples of that. But, SAE and SAE classifies self-driving level 0 through 5, right? As well as NHTSA 0 to 4. What Tesla is doing is strictly a level 2 system. That's all they've aspired to. And they've made this very clear. The driver has to keep their hands on the wheel and has to pay attention to the road at all times. So that's what we call an ADAS system, a level 2 ADAS system. What others are trying to do is jump to level 4. And I have some data of companies who are doing level 4 driving, and you can see how they're achieving it. But level 4 would be, the driver does not have to pay attention. And level 4 would be in certain environments, it's completely autonomous. Level 5 would be completely autonomous all the time.
Are you also working on solid state? If that can be doing, it becomes much lower in the cost.
Solid state has advantages, not huge ones in cost, but there are some advantages. And we've described our latest sensor as a solid state hybrid. So if you take the lid off our sensor, and you can't take the lid off of these, but you'll see that the laser detectors are completely solid state. And it will function as is without moving. The only reason we're moving it in 360 degrees is to save cost. If you think about it, every one of those lasers and detectors are firing 20,000 times per second. So we're reusing a laser detector 20,000 times in a second, rather than populating it with 20,000 times more lasers and detectors. But theoretically, you can create a pixel array. And as far as solid state is concerned, we are pursuing those sorts of options as well. But.
So how much data is generated, because the capacity of an Ethernet in a car is 100 megabits per second. So if you're going to use Ethernet, you need to compress it, or?
Well, right now we're 1 megabyte per second, and we're probably up to 2. So, yeah, the architecture is challenging. No, it's not necessary today, but as you add more sensors to a vehicle, these are considerations that need to be thought about.
So how much power this one will consume? Because you put it on some of these mobile.
Right. This one is drawing 8 watts.
Sorry, what's the safety level for, say, pedestrian very close to your car? Is extending a trip?
Yeah, it's a class 1 eye-safe device.
Okay.
So by a wide margin, so you can stare at it and look at it, and, it's not going to bother your eyes.
What's the wavelength?
905 nanometers.
How rugged is it? What's the mean time between failure for driving on a bouncy road that's going to induce a lot of vibrations?
I'm glad you asked that question because I got a little bit to show you there, but yeah, it's we have some pretty good case studies in it. I don't have an MTBF number as of today. Our aspirational goal for the automotive version of it, which we're introducing, will be 10,000 hours.
And that's good enough for AEC qual, for automotive qual?
Yeah, it's from our automotive customers, it seems to be.
Isn't that only 1 year? Okay. Yeah. Okay.
So this, you've seen this one here, but we. I've actually been told that at this point it's remote controlled for demonstration. And you can tell because the LiDAR is not spinning, But now you can see it's actually working. So, and it's perceiving boxes. So, you can imagine this might be a way to deliver packages at some point in the future, because the robot can now see very clearly in 3 dimensions using its LiDAR.
What's the standard RPM of the motor?
I'm sorry, can I?
The RPM of the motor?
You can go anywhere between 5 and 20 hertz. It's adjustable. So, this is an example of how LiDAR can be used for people tracking and for security. So here it's done in conjunction with a camera. So if a camera, you can see the camera on the bottom, the LiDAR on top. If a camera's looking at a scene, that's a lot of data to parse and to figure out what's going on in a scene. So here's a shot of what a LiDAR would see. This is a 3-dimensional model, and it's seeing people. And you can track, for Raytheon software, you track individuals. So if somebody goes to an odd place or is exhibiting suspicious movement, then it will alert the camera, focus on this person. So, see the example of this young lady here who was walking around, doing something very suspicious, obviously. But you can see it catches her right there. Sees her going to the booth she's not supposed to be going to. And then the camera will be trained on her at that point. So this is it's just one example of how security can be enabled and made a lot easier through LiDAR. Tracking her through that.
Maybe I missed the appreciation, but you could see the same with a camera too, right?
There's a lot of data for a camera to take into a scene. A camera can't catch everything that's going on, just too much data. And, yeah. You know, I'm primarily here to talk about self-driving because that's my own piece of business at Velodyne. And after DARPA Challenges, we saw participation, or we saw installation of these on military vehicles. Military applications a little bit different. Rather than trying to do object identification in a scene, these guys are trying to see an object and decide, do I run over it or do I drive around it? But it's a similar idea. You need a very good 3D model of the environment to make that decision. You know, since I started at Velodyne, people ask me, so when can I buy a self-driving car? And if you have a few $1 million and a good contact at Caterpillar, you can go buy one of these things. This is about a 10-meter tall a mining truck, completely autonomous, no driver inside, that drives in Australia today. And they've been driving for about 5 years. A very rugged environment, to your question. Very high vibration. Now there are major automakers that are starting to put LiDAR on their level 4 test vehicles. Most obvious one was the Ford vehicle. They've announced that their entire fleet this year will have the 32 sensor on it. But several other customers are on here as well. You can see our sensors on it. And so why do they need a high definition LiDAR? Well, this is an interesting study that came out of Car and Driver. And it was a level 2 driving systems. It evaluated the level 2 systems. So it had an 80-kilometer course, and these numbers in red here say how many times the system disengaged in that 80-kilometer course. In other words, how many times did the driver have to take control of that vehicle? And the best performer, not surprisingly, it's a really good vehicle for level 2 driving, is the Tesla. But still, in an 80-kilometer course, 26 times it had to disengage. So every 3 kilometers, the driver has to take control. I don't know if there are any Tesla drivers out here, but this was a particularly challenging course. And then, you know, the Infiniti Q50, 93 disengagements in any 80 kilometers. So once every kilometer, you have to grab that. And that is just for lane keeping, nothing else. Just to be able to see this line on the lane. That's a big challenge in and of itself. So the car companies who were moving to level 4, you know, they realize there's business to be made there. They're seeing all these robot taxi companies moving out there, and these shuttle companies, and they realize they have to be in that space as well, because if they don't, they're probably toast. So with a level 4 system, this data is available at the California DMV. It's really cool because California is the only place in the world that requires data to be recorded. And what data they require is anyone who has a level 4 driving license in the state. Those are these companies here. Tesla also has a license to drive, level 4. Notably, they're missing from reporting any data, which, you know, you can draw your own conclusions based on that. But they have to report how many miles they've driven and how many miles between disengagements, right there. And it's really no contest. There's only one company that's using, that up until 2015 used 3D high definition LiDAR, and that was Google, and remarkably, they're driving almost 2,000 kilometers, and this was as of the end of last year, 2,000 kilometers between disengagements. That's a remarkable achievement. I mean, just the year before they were at 100 kilometers roughly, or 200 kilometers. These other guys, using radar, camera, ultrasonics, 2D LiDAR, no one's above 40 kilometers.
So,
And these guys, by the way, are mostly driving on the highways.
Is
yeah,
it,
but the Google one has the map, right?
Yeah, that's right. Their approach is use the prior map and localize against, and I'll show you how that works right here real quick.
The other guys don't have the map, right?
I don't know exactly specifically what they're doing, but I could imagine they have to have some sort of mapping to do self-driving. You have to have some sort of mapping, no doubt.
so they have a more extensive mapping.
Yeah. So this is a video of Ford at M-City. It's kind of a Potemkin village near University of Michigan. And they developed this prior map. So this is the LiDAR. You can see the 3D map with this. And it's kind of dark, but everything you see here is LiDAR data. Nothing else. No camera, no radar, no nothing. Just LiDAR. So what they do is they've got this prior map, and they're going to match the, by the way, you can see the white lines on the road, that's all LiDAR data too. So the reflectivity lines just pops out. And that purple line now, that's the live sensor feed. So you're localizing against that. And you're capable of matching up within centimeters, 3 centimeters or so. So that's a highly accurate way to make sure you're exactly where you need to be on the road, laterally and longitudinally. And also, it helps with, you can track dynamic objects in real time, so you can see the person. That's 3D data, so you know exactly the volume of that thing, and you know the velocity of it moving, so it's pretty easy to guess what it is. Where there's a 2D image of a camera, you know, good luck with it. And here, this kind of shows how they're localizing against the ground. You don't need light to do it. It's immune to light. So this is something they call night autonomy. You can see the laser lines on the ground here. Pretty cool. And the laser lines are matching up against the prior map here, so you can drive completely in the dark. Now, what happens if that road surface is covered? That's the 2D, they're doing a 2D matching. They're matching to the ground plane. But if you can't see the road, for example, in the case of snow, like this, they've also done a demonstration in snow. So here they're matching the LiDAR data to the 3D data around the vehicle. They're not looking at the road anymore. They're looking at 3D structures around the vehicle. And they're able to drive and navigate fairly well with that as well. These are just demonstrations, but this kind of gives you an idea of the power of LiDAR data doing these sorts of things. So last slide here. So what are the challenges to make it automotive grade? You got to reduce the form factor. From the first sensor we made was 1 meter diameter. Now you can see it's a lot smaller. Reducing the weight. First sensor was 30 kilograms. And this one here is an 830 gram. Now we have a 590 gram one. Reduce cost. From $85,000 sensor, we see a route to get to a $500 sensor with our automotive version of it. And range and resolution. This year in 2016, we've introduced a VLP32, which has a 200 meter range. So allowing higher velocity travel, which is very key. So that was all I got for you. If you want to stick around, I'll do a demonstration of this. You can see what everyone looks like in LiDAR data.
Yeah, I'd like to thank John.